Okay, we're going to start in about 1 minute.
Okay, slide on over here. All right. Hi, everybody. From the imaginary shores of Lady Bird Lake here in Austin, Texas, welcome to today's session of Greg McMillan's live process control seminar and demo series. And we call these Deminars for short. Today's topic is Control Loop Performance Primer, the what and why needed to improve 90% of the loops. And the broadcast is being recorded and will be available for future viewing. We'll be muting all but Greg's microphone, so please use the Q&A box to ask your questions of Greg, and I'll relay them verbally to him during the course of today's session. And we'd like these to be as interactive as possible, so as questions occur, fire them away in the Q&A box, and I'll relay them to Greg. With that as a preamble, let me turn things over to Greg.
Thank you, Jim. Well, these Deminars are sponsored by Emerson Experiotech and Mina, and they're created by me and Jack Ehlers. Jack is a process control specialist at Monsanto in St. Louis. The website was created by Charlie Schleiser at csdesignco.com. This is me. And I got a top 10 list from Hunter Vegas for the October Control Talk column, and it's the top 10 things you don't want to hear during startup. Number 10, we never really could figure out what the old system was doing. Do I have a system backup? I thought you were making backups. We want to make our startup into a reality show. The displays are fine and dandy, but where are the panel boards? We've changed our mind. We want the old system back. Can you reprogram it so the wrong valve still works? Didn't you get the revised batch sheets? Is a blue screen bad? What is that burning smell? And the number one thing you don't want to hear, we're out of coffee. So, to give you kind of background, the way I see it, there's no clear picture of what is the potential source and size of process control improvement on a general basis. Practical process control knowledge is detailed, fragmented, and is experience-driven. This seminar will attempt to provide a unified approach and understanding of the impact of the PID, final control element, valve, or variable speed drive, the process disturbance, and the measurement on loop performance. And we're going to do this in less than an hour. Unifying concepts. Well, it's all about management of change, whether it's intentional change in terms of subpoints that occur during startup or batch operation, during transitions, during optimization, or whether it's unintentional change as a result of disturbances that are either coming in from other parts of the process. It could be ambient condition related, it could be raw material related, it could be due to, as we see, valves that are acting badly, or to control loops that are tuned perhaps too aggressively, or due to some interactions in general. 90% of the process control improvements involve the following concepts. Delay, speed, and gain are the big three, and we're going to spend most of the time today on those. Then hopefully we're into the things that are becoming less of an issue, although I can't discount the fact that some plants still have sensitivity, resolution, and backlash and deadband problems, principally with their final control elements, valves and variable speed drives. And then there's the nonlinearity that's always there. We have noise, and we have oscillations, principally as a result of control loops and bad valves. And we can have resonance as a result of those oscillations. And what we like to do is have control systems and volumes designed to attenuate those oscillations. And lastly, there is, of course, the opportunity for optimization, and to realize a lot of the benefits you get from making these improvements, you often have to change your set point. So delay, speed, and gain are the most prevalent limiting concepts. We'll spend the most time on those. Delay. Without dead time, I'd be out of a job. I said that a long time ago, and since I still have a job, we still have dead time in all our loops. The only place where you don't have dead time or negligible dead time might be in aerospace or servo mechanism control, or in sometimes some loops that are created in a university, theoretically anyway. End up with just a single time constant and no dead time, and you can do principally anything you want with those loops. But in real life, we have dead time, and the fundamentals here are a more descriptive name would be total loop dead time. The loop dead time is the amount of time for the start of a change to completely circle the control loop and end up at the point of origin. For example, an unmeasured disturbance cannot be corrected until the change is seen by the controller, and the correction arrives in the process at the same point of entry of the disturbance. While process dead time offers a continuous train of values, whereas digital devices and analyzers offer non-continuous data values at discrete intervals, these delays, all of these delays add a phase lag and increase the ultimate period, decrease the natural frequency, like the process dead time. Our goals are to minimize delay. Wherever it is, the loop cannot do anything until it sees and enacts a change. We have pure delay from dead times and discontinuous updates. In the process, piping, duct, plug flow reactors, conveyors, extruders, spin line, sheets can all have transportation delays, where a change at point A takes time for it to be transported to a point B, perhaps where it is measured. And this transportation delay for, say, a lot of this type of equipment, like piping and ducts and plug flow reactors, could simply be the volume between point A and point B divided by the flow rate. We also have digital devices today, and hopefully the scan, update, reporting, and execution time is small compared to the process dead time. And on the average, the amount of dead time that we would, or delay that we would get from these scan, update, reporting, and execution times, on the average can be considered to be about half of that time interval. Then we have analyzers, and they can be a source of a much larger dead time when there's sample processing and analysis cycle times. And there, since the result is made available at the end of the cycle time, whereas with digital devices it's usually right near the beginning, because it's at the end, we actually have more effective delay from that, and you really would need to take 1.5 times the total sample processing and analysis cycle time as the amount of delay you would get in the control loop. And then we have sensitivity and resolution limits, and people don't realize often that these create dead times because during a lot of the discussion in the literature and the tests that are made, they make step changes. And if you make a step change large enough, you won't see the dead time from either the sensitivity and resolution limit or from backlash and deadband. But controller outputs usually are ramping rather than stepping. And so the ramp through these limits takes time. And you can estimate the dead time as the value of the sensitivity and resolution, or backlash and deadband, divided by the rate of change of the controller output. So the faster you tune your controller, the less you're going to see in terms of delay from the sensitivity and resolution, backlash and deadband. And then we got equivalent to delay from small time constants, small lags, and series. In the process, it's due to mixing. We don't have perfect mixing, so we've got lags associated with that. The big source of large lags is, of course, if you have a distillation column or any type of column where you have a whole bunch of trays, and each one of these trays are like a relatively well-mixed volume due to turbulence and bubbles. And so you have all these volumes in series, and they create lags, and as a result, these lags in series create dead time or delay in the process. Then we have heat transfer lags. We have thermal well heat transfer lags as well. We have electrodes, pH electrodes. They're normally very fast, but if they get a little bit of coating or they get aged due to high temperature or just being in service for a long period of time, those electrodes suddenly can go from a lag of 2 seconds to, say, 100 or 200 seconds. So you can get several orders of magnitude increase in the lag of the electrodes due to aging and coatings. And then we have transmitter damping settings that are usually negligible, but for compressors and for very fast pressure control loops, they can be critical. And I know one person sent me an email and said that he related a lot of his compressor control problems and shutdowns to the fact that the default settings from one manufacturer of DP transmitters had a damping setting that was over a second. Now, that doesn't seem like a lot, but if the process can change very rapidly in less than a second, then 1 second transmitter damping can be a killer. Then finally, we have signal filters, and you can get fooled by thinking you are doing better by smoothing everything out, but you are then not seeing the real process. And we do have an equation later on to show how you can figure out maybe what the real process is doing if somebody put in a big signal filter. Or you can use the same equation to see the effect of volumes that act like a filter of oscillations. Anyway, the other parameter that is very important is speed. And I first started to think of, well, I could say time constant, time lag, but then you got integrating processes, and you got all different sizes of time constants, and really what we're looking at is the rate of change of the process, principally in the first 4 dead time intervals. In the beginning, when the controller has to do most of what it can do. The thing is that speed kills. High-speed processes and disturbances or low-speed control systems can kill performance. So the fundamentals here is the rate of change in 4 dead time intervals is most important. And we'll see this for the 3 major types of processes. By the end of 4 dead times, the control loop should have completed most of its correction. Thus, the shortcut tuning method in Demonar 6 is consistent with performance objectives and this fact that the speed, the rate of change initially, right after you start to see the response, is what's most critical. Our goals are to make the control system faster and make the processes and disturbances slower. I remember taking a graduate course in distillation column control and I was told by the professor, oh, this process is really bad because it is so slow. And I'm thinking, wow, slow process, man, I can tune my controller to take advantage of the large process time constant. And it turns out for distillation columns, a large process time constant is about 5 times larger than the dead time. And if you tune the controller, to be aggressive, it means that you can catch up to these disturbances a lot better, since the column is responding slowly. And so you got to be careful. Some people use slowness as a term for dead time. I'm using it for, you're seeing a response, and what is the rate of change of the response? If the rate of change of the response for the process and disturbances is slower, that's a good thing. What are the sources of the speed? Well, for the control system, it's the PID tuning gain rate. And so as you make these settings more aggressive, faster, you get a faster rate of change of the controller output and a faster correction. Then you've got the slewing rate of control valves. There's normally not an issue except for very big control valves or very fast loops. Then you have the velocity limits of variable speed drives that are imposed in the setup of the drive electronics. And this is done probably to a greater extent than we realize. And as a result, a variable speed drive, the rate of change that you can make in a flow through a variable speed drive may be a lot slower than what you can get from a control valve due to these imposed limits, velocity limits in the electronics of variable speed drive. And we have disturbances. Worst type of disturbance is a step disturbance, and we get those from batch operations, on-off control, manual actions. That's a good reason why you want to automate a lot of your processes. And in particular, by automate, I mean putting in control systems, because hopefully the control system doesn't make step changes, but is ramping corrections. Similarly, you have problems with safety instrumentated systems whenever they take discrete actions. Startups and shutdowns, if you allow a lot of trains of equipment, and these trains of equipment are going up and down, they're creating almost step changes. So what you would like to do, say, instead of batch operations, is to put in fed batch operations. And instead of on-off control, like where you have level switches turning pumps on and off, put in a level control loop. And wherever an operator is making an adjustment of flow, consider, can I put in a PID loop to do that? And on startups and shutdowns, can you get the PID control as soon as possible, rather than having the operator making or sequences making abrupt changes, trying to guess what needs to happen. You get oscillations, principally from limit cycles, from bad acting valves, interactions, and excessively fast PID tuning. If you tune your loop right, for the most part, except for startup and major set point changes, you'll be seeing mostly the effect of reset action in the PID in terms of correcting for disturbances. In the process, we want the speed to be as slow as possible, and we get that from better mixing and bigger volumes. The mixing is provided by agitation, boiling, mass transfer, diffusion, and migration. So what this means is, even if it's not an agitated tank, if you have a large enough tank and a big enough residence time there, just due to diffusion and migration and tendency of chemicals to go from areas of high concentration to low concentration, we'll end up with mixing and blending, unless there is some layering that's going on due to density changes between components in the tank. The third concept is gain. It's everywhere in the loop. All is lost if nothing is gained. If you had a zero gain, you wouldn't be able to see what's going on. So a zero gain anywhere in the loop would be, of course, disastrous. We don't see that, but we do end up sometimes with control valves being on the very flat part of their installed characteristics, and we say they're losing their sensitivity. Really what they're doing is we're ending up with almost a zero gain for that final control element when it's way out on the flat part of the installed characteristic. And this occurred quite a bit when we were trying to push plants way beyond their normal operating plant operating set points that they were designed for, and we end up with valves on the flat part of their installed characteristics, say rotary valves up there around 80 to 90% open. Fundamentals. Gain is the change in output for a change in input to any part of the control system. Thus, there is a gain for a PID controller. We're probably familiar with that, but also with the valve, disturbance, process, and measurement. Knowing the disturbance gain, the change in manipulated flow per change in disturbance is important for sizing valves and for feed-forward control, and for control system analysis. Our goals are to maximize the control system gains, maximize the control system reaction to change, and to minimize the process and disturbance gains, minimize the process reaction to change. The sources, PID controller gain, inferential measurements, the temperature change for a composition change in a distillation column. Now, this is one case where the gain needs to be increased because it's an inferential measurement, and if you don't have much of a temperature change for a composition change, then you're not going to be able to use temperature in the control loop as a way of controlling the composition of the column. So it is a case where in inferential measurements, you got to make sure that whatever you're using as an indication of what you're really after, which is often a composition, it has enough of a change for the composition change to be indicative of what's going on. The slope of the control valve or the variable speed drive installed characteristic, that's going to be the gain, and it depends upon the inherent characteristic in the system loss curve. And you have to be particularly careful with variable speed drives with high static heads. You may run out of really process gain there at the low speeds much sooner than you might think. Measurement calibration, the gain there is 100% divided by the span. It's important where accuracy is in percent of span. With smart instruments, it's not so much the case, but in general, if you want to have a lower measurement error, you try and narrow the span to just cover your operating range of interest. And of course, process design is going to affect the process gain, and that's beyond the scope today. Attenuation by volumes, and we're going to see how we can estimate that, is going to actually reduce the gain of ultimately maybe what's downstream that you're interested in. The attenuation by PID and the transfer of variability from controlled to manipulated variables is going to, again, attenuate and change the gain associated with what may be happening downstream that you're ultimately interested in. Now, hopefully today, sensitivity and resolution is not so much an issue. With the new DCS systems, we have much greater A to D resolution, and with new measurements, smart measurements, we have better sensitivity, and with digital positioners and the newer throttling valves with diaphragm actuators, we have good sensitivity. The thing is, you cannot control what you cannot see. Fundamentals are the minimum change measured or manipulated, and once past the sensitivity limit, you see the full change that you need to detect, or in the case of manipulation, that you need to use. However, a resolution limit is different, and a resolution limit will quantize the change. And it's very common in the literature for people to say resolution when really they should be saying sensitivity. So, you know, it's nice to know the distinction, because actually a resolution limit would be more severe, because you're going to get a step response, and you're not going to get those intermediate values once you get past the resolution limit like you get once you get past the sensitivity limit. Both will cause a limit cycle if there's an integrator anywhere in the process or the control system, a single integrator. The goals. Improve sensitivity and resolution. In measurements, minimum change detected and communicated. For example, the sensor threshold for its ability to do its job, and the wireless update trigger level, and then again the quantized change that you get from A to D and D to A converters. Then for final control elements, it is the minimum change that can be manipulated. For example, control valve, stick slip, sensitivity, and speed resolution. Backlash and deadband. It's no problem if you don't ever change direction. So the minimum change measured and manipulated once the direction is changed. Once past the backlash deadband limit, the full change is seen or used. Both will cause a limit cycle if there are two or more integrators in the process or control system. In other words, it's not commonly known, but a cascade control system on a self-regulating process will have a limit cycle from backlash deadband if both the primary and secondary loops have integral action. So we should minimize backlash and deadband. Sources, hopefully we don't have any more pneumatic instruments laying around. Installed. They may be laying around. Hopefully they're not installed in your process, because the flappers, links, and levers have backlash and deadband. Rotary valves and dampers are notorious for backlash and deadband due to their links, connections, and shaft windup. Variable speed drive setup parameters often put in a deadband to eliminate hunting and chasing noise. Nonlinearity. Not a problem if the process is constant, but then again, if the process is constant, you don't really need much of a control system. Fundamentals, while normally associated with a process gain that is not constant, in a broader sense, a nonlinear system occurs if a gain, time constant, or delay changes anywhere in the loop. All process control systems are nonlinear to some degree. Our goals are to minimize nonlinearity. Sources are the control valve and variable speed drive installed characteristic, particularly with valves that have a flat characteristic at high flows. For variable speed drives, it could be at high static heads and low speeds. Process transportation delays, it's inversely proportional flow. Digital analyzer delays, where the loop delay depends upon when the change arrived in a discontinuous state of value update interval. But we have ways of approximating it on the average, as I mentioned, as either half or 1.5 times the time interval, depending whether you're talking about a digital or analyzer. Inferred measurements, conductivity or temperature versus composition plot is a curve, but it's not a straight line. Exponential relationships, for example, the glass pH electrode and zirconium oxide oxygen probe. And process time constants that are proportional to volume and density. Noise, the best thing you can do is not react to noise. Fundamentals, extraneous fluctuations in measurements or manipulated variables can be the source of noise. We want to minimize the size and frequency of the noise and do not transfer noise to the process. I think actually what I meant to say here in terms of frequency of the noise, well, it kind of depends where you are in terms of the control loop, which we'll see. Sources are bubbles, concentration and temperature non-uniformity from imperfect mixing, electromagnetic interference, ground loops, common problem with pH, interferences, say with sodium ions and pH electrodes, velocity profile non-uniformity for a lot of flow measurements, and the velocity impact on pressure sensors. Oscillations. Oscillations are best kept in control theory textbooks. Fundamental, sine waves, square waves, sawtooth, periodic disturbances can perpetually upstate a system and get amplified by resonance. We should minimize the source and attenuate by controller tuning and process design, principally volumes and mixing. Limit cycles from sensitivity, resolution, backlash, deadband, on-off control, aggressive tuning, and part of this is interactions, and then excessive reset actions that we get particularly common for level loops. Resonance. Don't make things worse than they already are. The oscillation period is, if it's close to the ultimate period, it can be amplified by feedback control, make the oscillation period slower, or make the control loop faster. Control loops in series with similar dead times, like multiple stage pH control, are a situation that could end up in resonance. And control loops in series with similar tuning and valve stiction and backlash. And a much slower oscillation, say from day to night ambient temperatures, but these can be a problem to slow loops like on very big columns that may have take a date or two to line out after a disturbance. Here, the day to night changes can end up causing continuous oscillation. Attenuation. If you had a blend take big enough, you would not need control. Ran into that in some spin lines. We spent a couple of days in there, but almost immediately we found out the polymer pumps were maxed out from all the different polymer lines. And I said, well, you have no control. And I found out, well, they had these huge blend tanks, and they were able to blend out the differences. And after 10 minutes, they decided there was no opportunity, but we had to stay for 2 days to follow through. Anyway, attenuation increases as the volume of the blend take increases and the ultimate period of control loop decreases. We have an equation for that. We can maximize attenuation by increasing volume and mixing and making loops faster. So the sources of attenuation are the mixed volume size and degree of mixing, and also control loop speed. Optimum. This is a whole subject in itself. Most set points are not at their optimum. The fundamental is the primary loop set point is offset from the optimum temperature, pressure, concentration. We should minimize this offset. The sources of the non-optimum operation, the most common one cited is process variability, but we have other things like measurement error, sensitivity, resolution, and backlash deadband, limit cycles. Lack of process knowledge is a big one. Process nonlinearity, so you can't feel comfortable with an adjustment on a continuing basis being valid. Operator preference, they have sweet spots, so it goes along with lack of process knowledge and process training. And then there are some incorrect safety instrumentated system settings that cause you to back off from the optimum when you really don't need to. So we have different types of processes. The three principal types of processes are self-regulating, and here again I would say it's the maximum speed in the first 4 dead time intervals, and this is true for the more interesting loops. You could say for a flow loop everything's going to happen so quickly that this is really not applicable, but I'm more interested in the tuning of the temperature loops, the vessel pressure loops, and concentration loops and pH control loops. And for those, we get into much slower responses, larger process time constants. So again, though, we do have a delay. We do have a process time constant. In this case, it's a negative feedback time constant, and that determines the speed here. We also have a process gain here, and if you're going to use it for tuning the controller, you have to make sure everything is in percent per percent. So therefore, instead of PV, which is in engineering units, I like to use CV for control variable, and its units are percent. And similarly, instead of controller output, which can be in engineering units, I like to use CO, indicate I'm talking about percent controller output. Then we have the integrating process, and we still have this observed open loop dead time. Of course, these tests are done in manual, so that's what I mean by open loop. And then we get clearly into a ramp rate. And the maximum speed for dead times is the critical speed that we should use for analyzing and tuning for the integrating process. And here the integrating process gain is the change in ramp rate and divided by the change in controller output. Again, making careful you're talking about percent, so the units are percent per second per percent. Of course, the percent cancels out and the units then are 1 over second. Very important in terms of getting that right for the tuning of the controller. Lastly, and this isn't very common, we have a runaway process, and we still have this observed open loop dead time. But now we have a positive feedback time constant. Most of the time you can't have the test on long enough to see the acceleration that occurs with the positive feedback time constant, because for safety reasons the tests are terminated if you are in the open loop after 4 dead times. Probably a safer way of doing this test is to do it in a closed loop and make a set point change, and these loops typically have high controller gains, and so you're mostly going to see a step change in controller output from the high controller gain, and you're going to see then a response this ramp rate, and you're going to take the maximum speed there, and you can then kind of tune it with the shortcut method tuning settings, but you have to make some adjustments, as we'll see, for the reset time. This is a block diagram showing you all the different gains, for example, that there are in the loop, and really you need to multiply those all together to get the open loop response. And then we've got all the delays, and the small lags in there. Hopefully it's a small lag in your control valve, small secondary lag here, and got delay. Hopefully we get a big, nice process time constant lag here, and tau sub P2. But then we have lags here and delays here, and lags here, another delay here, and lags and delays. So if we sum up all of these, we end up with our first order approximation for the total dead time in the loop. Now, this is a nomenclature we're using. So let's go and see the impact of fast and slow disturbance, and we're going to do that for a self-regulating loop. First of all, we're going to review the fast upset test, primary upset lag, and reset time are both set at 6 seconds. Then we're going to increase the primary upset lag to 60 seconds and see what happens. Well, we're going to do this in the single loop lab that's available on the process control website. That's this website. We only have 2 virtual plants available because we're in the midst of making improvements, and it turns out with the remote desktop entry that we have, IT departments typically at best only allow the ports that we've got assigned for virtual plants, number 1 and 2. We actually have 16 virtual plants, and we're working on a way of making these virtual plants accessible without having to go through these ports that are blocked by IT. And so we're looking forward to that, to make all the virtual plants available for free use by people. Well, let's look at what we have in terms of an oscillation. I set up a test and simply do that. all I had to do here was go to the test mode. Normally we're in the explore mode when we're looking at things. And here in the test mode, and we have this square wave. However, the square wave disturbance it has a time constant associated with it, and right now it is 6 seconds. So we're going to change that to 60 seconds. And we're going to let that develop over a period of time, and while that's happening, we'll go back to the seminar. Now, what people probably don't realize is that there is a practical limit to controller performance. And, I personally concentrate on minimizing dead time, but it turns out that if you don't concentrate on tuning the controllers as fast as necessary to meet your objective, you're going to end up not doing as well as you think, based on the amount of dead time that you designed into the system, and that may have cost you a lot of money, or maybe not a lot of money, but some money in terms of doing a better process design. And you're not going to see the benefit of that if you don't take advantage of it by tuning the controllers faster, or at least as fast as necessary to meet your objective. And this first equation here I got from Peter Harriet, and it's really for a proportional only controller. But then again, most of what you see as a peak error really doesn't depend upon reset action, because reset is ramping over a period of time. Most of what you get is, in terms of reducing the peak error, is more immediate, and that's from proportional action. And so all of these equations are a rough estimate. Gosh, things are changing so much anyway, but so you shouldn't expect, accuracy is better than maybe 20% here, but it gives you an idea, maybe more importantly, of concepts of what's going to happen. In other words, in order to minimize the peak error, you really have to increase the controller gain. Now, sometimes peak error maybe isn't important, but when it is important, it can be maybe the one thing that causes the most grief and the most economic value that you need to go for, because peak errors are associated with staying away from safety instrumentated system trip settings, relief device. For example, if you have pressure control and you get the peak in pressure that's too large, you can activate relief devices, rupture discs, relief valves. If you have a temperature that's too high, you could actually trigger a runaway reaction or shut down. And so when you do have a peak error that's too large, the economic consequences can be quite significant. Now, for integrated error, it turns out that you want to decrease the reset time as much as possible, besides increasing the controller gain. So here you have an interesting situation where if you're more interested in the peak error, you could perhaps end up with the same integrated error by going with a higher controller gain and a higher reset time. You'd end up with the same integrated error, but you would end up reducing your peak error. Now, another important thing to realize is these equations, and particularly the peak error equation, is not really that accurate for a totally dead time dominant system, where the total dead time is much greater than the process time constant. If you have that case, the peak error here is pretty much going to be what is the open loop error, which is the error if you had no controller. In other words, for a dead time dominant system, you're going to see the full error from a step change that occurs as disturbance. Fortunately, a lot of disturbances are not steps. But that's the way we study it in control theory textbooks. Peak and integrated errors cannot be better than the ultimate limit. The errors predicted by these equations for the PID plus, which we looked at in Deminar number 1, and for dead-time compensators that we're going to look at in the next Deminar, number 10, cannot be better than the ultimate limit set by the loop dead time and process time constant, which is what we have here on our next slide. And here the peak error is proportional to the ratio of the loop dead time to the 63% response time, which is in the first order approximation is that loop dead time plus the primary process time constant. You can see here for dead time dominant systems, it tends to work towards the peak error being equal to the open loop error for a step disturbance, but you know, it doesn't really nail it. The integrated error is proportional to the loop dead time squared. And in the denominator again we have the 63% response time. So you can see how dead time is really very detrimental to the integrated error. And this approximation can be seen as a result of placing the optimum response, which is two right triangles next to each other, and the base is the dead time, and the altitude is the peak error. And so you can get at the equation this way. There's a number of other ways in Advanced Control Unleashed and in my current ISA paper at ISA Automation Week, first week October, that goes into the derivation of this. For a sensor or signal filter that is much larger than process time constant, in other words, you know, this big time constant here is not really in the process, we can get back at what's really happening in the actual process variable by use of an equation we're going to see later on. Now, what about the effective disturbance speed? It's kind of hard to estimate, but here we can get a rough approximation by saying instead of the open loop error we have from a step disturbance, we now have an exponential response. And that exponential response is basically how far does it go in terms of seeing that error, that open loop error within the process dead time. Because again, the control system cannot do anything to correct for a disturbance in that dead time. It can't see what's going on. It can't enact a corrective measure at the right point in the process in that time. So during that time, the disturbance is traveling, and you can estimate how far it's gone in that dead time interval as a way of getting at what is the actual load disturbance error that you're going to be working with. So you would substitute that in the equations for E sub O to get the effect. Then if you want to look at, hey, the attenuation by volumes, you can use this equation, and this assumes that the time constant here is much larger than the oscillation period. And I mentioned, you know, you can use this to get back at the original oscillations if you happen to have had, and this is normally undesirable, a very large signal filter. And so what you're seeing in your trend charts is a filtered amplitude, and you want to get back to the original amplitude here. So it's a convenient equation not only for signal filters, but for looking at the effect of electrode or thermal lags. You know, an electrode that has suddenly a 200-second time constant, at least on a static mixer, it's going to be looking like it's drawing almost a straight line in pH if there's any sort of buffering in the system. And, you know, and you may think, oh boy, things are going really well, until you notice that the period is really very large. And if you use this equation, you can get back to, wow, the original amplitude here before the filtering by the large electrode time constant is really bad. And one war story is They had an extruder, and they put the relocated temperature sensor from the melt into a wall with a massive block of metal, and the amplitude of the temperature oscillation was a lot less, and so the edict went out, install all the temperature sensors in our extruders in the massive block of metal rather than the melt, because the trim choice looked so much better. Well, the product quality deteriorated, and they got clued into the fact that they were seeing a very attenuated version of the real world. Okay, we're going to go back now to see what happened as a result of using a 60-second upset. Well, what we're most interested in here is the dark blue. And you can see we've got things are looking a lot better now that we have this big, well, relatively big. We could even have a slower disturbance than this in terms of the speed of the disturbance. So this is where we were with a 6-second time constant on the disturbance, and this is where we are with a 6-second time constant disturbance. And this is some of the clue why on bioreactors they can't see what's the control problem you're talking about with pH and temperature. You know, it's really hard for them to relate to, you know, even do I need to improve controller tuning? Well, their disturbances are not, you know, have time constant of 60 seconds. They may have disturbances that are days. They could be a 24-hour time constant, since their batches may take 2 weeks. So, you know, it's good to know that, you know, even though control theory textbooks all concentrate on step disturbances, in real life, hopefully, we've got these slowing down of disturbances, and so we have a speed of a disturbance principally by the introduction of good PID control. And the other thing, I guess, you know, it's important to know is in model predictive control, there is a penalty on move, where you can actually decide how quickly you want to make a move, and particularly for interactions, slowing down the move that you make can smooth things out, and particularly appropriate when dealing with very slow processes. So we'll go back to the seminar and wind up here, hopefully, pretty quickly. So there's an implied dead time from slow tuning. And this is something very few people realize, and that if you tune a controller really slow, you can kind of screw up in terms of adding filters and delays and scan times, and you're not going to see it. And so any sort of analysis that's done on the effect of adding delays, it really has to take into account how was the controller tuned. If the controller was tuned sluggishly, you know, in the extreme, you can almost approach manual operation. You're not going to see that. For self-regulating processes, we can use this equation here approximately, and we can use the lambda, which is the closed loop time constant, as we go slower, and lambda gets much larger in comparison to the loop dead time. We end up with an implied dead time that's significant. And here in this test, I had a process dead time of 10 seconds, and I was saying, well, how much analyzer delay can I add before I start to see some degradation? Here I used a lambda of 20 seconds. And so the equation would predict that I ought to start to see an effect once I had added about 5 seconds of delay to the existing 10 seconds, so that I was approaching the implied dead time that was in the system. Well, here we start out with a sample time of 0 seconds. Now we increase it to 5 seconds, and notice there is really no noticeable response. Now we increase the sample time to 10 seconds, and I guess this really wasn't an analyzer. This was maybe more like a digital device delay. And so if we take half of that as the actual delay, say that's 5 seconds, we should start to see the change. And we do. I probably should have had another one here showing you the effective sample time of, say, 15 seconds. It is quite noticeable at 20 seconds. The point of the matter is here that if you were to tune this controller with even a larger lambda, you wouldn't see the effect at 20 seconds. You could introduce more delay and not see much degradation in control. And so the effect depends upon tuning, which leads to a lot of misguided generalities that are solely based on process dynamics. If you're going to base it on process dynamics, you ought to say, this is the ultimate effect. But in terms of a practical effect, you need to take into account the controller tuning, because that's going to have an implied dead time in there. And you may have a good reason for tuning it slow, so I can't discount the fact that the tuning may be right for the control objective. It's just slow compared to what it ultimately could be based on the process dynamics. Now, what is the fastest possible PID tuning? Well, everybody has their favorite tuning rules, but they all kind of come down to the same sort of thing, at least in terms of controller gain. If you're trying to tune with a lambda pretty close to the dead time, which is about the fastest, which is the fastest you can really go, the lambda tuning equations would reduce to something similar to this. And what really changes when you go from self-regulating to integrating to runaway is just a slight increase in that factor from 0.4 to 0.5, 0.6. Now, a reset time, boy, there's, I can't, at least right now, unify all the different tuning methods. All I know is that for looking at trying to go with maximum disturbance rejection, then really what I want here is a very fast reset time. Now, if you're going for set point response, you may have to increase this reset time. But for disturbance rejection, the Ziegler-Nichols rule for a PID controller isn't too bad. However, for integrating processes, at least my experience says you need to double that. And then for runaway, and very few people have a true runaway, you have to be very careful about the amount of reset time. And I find that you have to have a reset time that is 10 times larger than, say, what you did for even an integrating process. Now, I'm not saying these are the settings you want to go for in your tuning. I'm just saying as a benchmark, if you want to compare your tuning settings versus the fastest possible in terms of how much better you could do if for some reason you could tune it faster, or you want to see the implied dead time, you can take into account where you are relative to the fastest possible tuning. This shows the effect of control loops either amplifying disturbances when they get close to the ultimate period, or doing nothing if they're so fast that it's almost like they're too fast. It's almost like noise. It's no better than manual. Here, if you're near the ultimate period, in terms of the oscillation period of the disturbance, you get amplification. Hopefully, you want that oscillation period to be way out here, much slower, and now you get into an attenuation, and the slope here of these lines are 1-to-1, and here this shows the effect of faster tuning. You can move over the break frequency and get more attenuation of your oscillation, and if you're, say, just close to the resonance point by making maybe the control loop faster, you maybe can move far enough away from it to actually provide improving control. Okay, well, we'd like you to visit the Process Control Lab website. We understand that IT restrictions are making this difficult. These are the advantages we think are offered by the website, and we'll be offering in a short course at Emerson Exchange use of the website, and hopefully by then we will have a way of getting in that IT is not restricting.
All right, well, we've got the Q&A box if you've got some questions here, but I did want to take a minute to say we'd like your feedback on today's session, and I put a little Q&A box with this URL that you can use to cut and paste, and it's basically a one-question survey and a comment field to provide us your feedback, and we'd love to have it. Okay, the next session, the next seminar will be October 13th, Wednesday, same time, 10 a.m. Central or 1300 UTC time, and the topic will be PID dead time compensation, how to set up and tune a PID for dead time compensation. And today's session will be taking the recording and making it available both on Greg's modelingandcontrol.com blog and my emersonprocessexperts.com blog. So if you have a colleague or someone else you think might be able to benefit from it, please point them over to one of our blogs here. And with that, let me turn it over to for questions here, and I'll be looking at the Q&A box and I'll relay them over to Greg.
I know there was a lot of ground to cover in a short period of time.
All right, well, thanks for coming, and we'll see you on October 13th.